Welcome to the archive recording of the joint press briefing by Fujitsu and Osaka University. On August 28th, Fujitsu and Osaka University announced the joint development of two new technologies for the quantum computing architecture that will accelerate the realization of practical quantum computing. In this video, we will explain the details of the developed technologies. The first speaker is Professor Keisuke Fujii from Osaka University. The title of his presentation is Introduction to Osaka University's Quantum Computing Research Activities.
Let me explain about basics and background of quantum computing to understand our achievement and also Osaka University's effort to realize quantum computers. I'm Keisuke Fujii, Professor of Graduate School of Engineering Science, Osaka University, as well as Deputy Director of Center for Quantum Information and Quantum Biology. Quantum computers use quantum mechanical effect to perform computations. Today's computer uses something called a bit to represent only states of 0 and 1. On the other hand, a quantum computer can take a superposed states of 0 and 1 using a qubit. For example, when computing n bits of information, there are 2 to the n states in total and need to be handled in classical computation. However, by expressing them simultaneously and using quantum entanglement, a quantum computer can be expected to achieve quantum exponential speedup compared to current computers for certain computational tasks. The realization of quantum computers is expected to make it possible to perform complex computations such as material designs, drug discoveries, financial engineering, and others, which are in principle difficult to perform with high precision and high speed with current computers. However, qubits are sensitive to noise originated from undesired interaction with its environment or imperfect control operations, and can make errors in computations. For example, even if each quantum gate operation succeeds at 99.9%, if such a gate operations are repeated 20 steps for each of the 50 qubits, the failure probability of computation rises to the 36.8%. To handle this, we can use the idea called quantum error collection, which protects quantum information by using multiple physical qubits redundantly to form a single logical qubit, so that we can collect errors which occur on physical qubit. Fault-tolerant quantum computing (FTQC) is a framework for performing computation while performing quantum error collection. In the conventional framework of fault-tolerant quantum computing, any computation is performed by decomposing it into 4 types of elementary operations on logical qubits called universal gate set. These 4 operations are quantum analog of the AND, XOR, or NOT, and so on in the current computer. For example, if we want to apply the phase rotation gate around the z-axis with angle of pi over 128, it is decomposed into the sequence of logical Adamo, S, and T gate in this way. These logical operations for universal quantum computation have to be done fault-tolerantly, requiring a complicated operations called lattice surgery. In the case of surface code, which are one of the most common quantum error correction code, quantum information is encoded in each logical patch, and error detection, so-called syndrome measurement, is repeatedly performed in unit cell consisting of the 4 physical qubits. Meanwhile, operations such as merging, splitting, deforming, and moving 2 logical qubit patches are realized by turning on and off syndrome measurements between the logical patches. By doing so, two logical qubits are correlated and logical operation on them is performed. This is the basic operation of lattice surgery. For example, the logical CNOT gate shown in the previous slide is implemented for logical qubit 1 and qubit 2 by using deformation, movement, merging, splitting as shown in this diagram. Osaka University established Center for Quantum Information and Quantum Biology, QIQB, as an initiative for quantum computers. QIQB is engaged in research in a wide range of fields related to quantum technology, quantum computing, quantum interdisciplinary research, quantum information devices, quantum communication and security, quantum measurement and sensing, and quantum biology. Specifically, Quantum Software Research Hub, supported by JSTCO Next, is focusing on the full stack of quantum computing, starting from quantum computing devices, control electronics, and software to handle them, and also applications of quantum computer. So Quantum Software Research Hub is one of the members of Japan's Quantum Innovation Hub, which is Japan's national strategic initiative for promoting quantum technology. So the QIQB Center plays an important role in the Japan's quantum technology innovation strategy.
The next speaker is Dr. Shintaro Sato from Fujitsu Research. The title of his section is Fujitsu's Quantum Computing Research Activities and New Technologies for the Quantum Computing Architecture.
I'm Shintaro Sato at Fujitsu. Here, I'd first like to explain Fujitsu's effort to realize quantum computing and then explain technologies we have developed for the new computing architecture. This slide explains our R&D strategy for quantum computing. We cover all the technology layers of quantum computing, from quantum devices, platform to application, with world-leading research institutions. We basically put emphasis on software technologies because we do not know the final solution for hardware technology yet. As for hardware, we work on a few different technologies. In fact, we work on the superconducting qubit technology with RIKEN and diamond spin qubit technology with TU Delft. We have also started to develop applications with end users by using a hybrid quantum computing platform consisting of a quantum computer simulator and a quantum computer we developed with RIKEN. Fujitsu is conducting joint research with Osaka University and established the Fujitsu Quantum Computing Joint Research Department in 2021 to mainly develop quantum software for Fortran quantum computing, which includes software for error correction and software for logical gate operations. Fujitsu is also focusing on human resource development in the quantum field as part of the Fujitsu Small Research Laboratory. As a result of the joint research, an original quantum computing architecture was established, and the press release and joint press conference were held jointly by Osaka University and Fujitsu in 2023. I'd like to explain this on the next slide. This quantum computing architecture enables practical quantum computing with fewer qubits than previously proposed FTQC architectures. In the conventional FTQC architecture, the operation called phase rotation, which is essential for quantum computation, is realized by a combination of logical H and T gate, and it requires a huge number of qubits and quantum gate operations. We have developed an original phase rotation gate. and incorporated it into the universal gauge set for the first time in the world. This allows phase rotation to be performed more efficiently than before. However, this phase rotation gauge error cannot be corrected, so the accuracy is somewhat limited. In the next section, I would like to explain our effort to put our original quantum computing architecture to practical use. This time, two major technological developments were carried out. One is to improve the accuracy of the phase rotation gauge described earlier, and the other is to implement this architecture in a quantum computer. I will first explain the purpose and effect of this approach. The purpose is to expand the computing scale of a quantum computing architecture and make it possible to apply it to practical computing. For example, when we estimated the number of qubits and the time required to calculate the Hubbard model, which is used for the analysis of high-temperature superconductivity, we were able to obtain an estimate that exceeds the speed of current computers with tens of thousands of qubits. So-called quantum advantage can be achieved. The calculation time of the Hubbard model with a 6x6 crystal lattice is equivalent to a current computer at 40,000 qubits, and an 8x8 lattice with 60,000 qubits can be computed in 10 hours versus 5 years for a current computer. That's 100 times faster. I would like to explain the details later. First, I will explain how to improve the accuracy of the phase rotation gauge to expand the computing scale. The challenge of our quantum computing architectures, which I mentioned a little earlier, is a limitation in the computing scale due to their limited accuracy. For example, in the condensed matter physics, it falls more than 2 orders magnitude short of the required scale for the Hubbard model analysis described below. In order to perform such practical calculations with our architecture, it was essential to improve the accuracy of the phase rotation gauge. In order to explain our technology, I will first explain in detail how phase rotation gates are implemented in our architecture. This is a quantum computer, and it contains a qubit chip with a row of physical qubits. Since the basic unit of computation is the logical qubit shown here, we consider phase rotating this logical qubit, which is composed of 5x5 physical qubits. The central figure shows the time lapse of the logical qubit. First of all, I will omit the reason, but the logical qubit and the calculation cannot be directly rotated. So let the answer logical qubit be rotated once. This is called phase angle generation. We are directly rotating the physical qubit, the answer qubit, and the data logical qubit are then interacted by lattice surgery to transfer the phase angle. This changes the data logical qubit to a rotated state. In principle, both the phase angle generation and transfer can fail with a certain probability, in which case we will repeat until it succeeds. As for the improvement of the accuracy of the phase rotation gate, we have developed a new technology for generating the phase angle in the ancillary qubit described earlier. I explained that phase angle generation directly rotates the physical qubit. Until now, the rotation of the physical qubit has been done at one position. But by making this redundant to multiple positions, the effect of a rotation error on the phase angle of the logical qubit is greatly reduced. As a result, the accuracy of the phase rotation gate has been greatly improved, and the computing scale has been expanded more than 1,000 times. The 1,000-fold increase in the computing scale makes it possible to analyze the theoretical model of high-temperature superconductors called the Hubbard model, which is previously impossible with this architecture. Large-scale analysis of the Hubbard model is expected to lead to the discovery of new high-temperature superconducting materials and in the future to a reduction in electricity transmission cost. Next, I will explain how to implement the new computing architecture to quantum computers for practical applications. Our quantum computing architecture is based on the rule of how to define universal gate set, and when solving a concrete computational problem, it is necessary to specify the rule of how to operate physical qubits. As introduced earlier in the section on lattice surgery, operations on logical qubits are very complex. In particular, the phase rotation gate transfers the phase angle generated by ancillary qubit, but simply implementing this may slow down the calculation speed. For example, if we try to phase rotate two logical qubits at the same time, the phase rotation on the lower side may continue to fail even if the phase rotation on the upper side succeeds only once. Then the upper side has to wait forever for the lower side to succeed. Thus, an efficient operation schedule that takes into account the phase angle generation and transfer failure is required. This time, we have developed a technology to reduce the effect of phase angle generation and transfer failures by dynamically utilizing qubits. Specifically, in the example here, if we assume that the upper side phase rotation is successful in one step, the upper side ancillary qubit becomes free in the next step, and it is reused to generate the phase angle for the lower side qubit. If the phase angle is generated successfully, it is transferred to a lower qubit. If this transfer is successful, it will save 3 steps overall. Though there is a possibility that the generation of the upper phase angle and the last transfer will also fail, but we have developed a scheduling technology that takes this into consideration and speeds up the entire process. This technology enables parallel execution of optimum phase rotation gate. For example, the diagram on the left shows the phase rotation of two logical qubits, which is expanded to 36 on the right. In this animation, the middle two columns are the ancillary qubits, and the outer two columns are the data logical qubits. The green is phase angle generation and the blue is transfer. The animation shows how these operations change over time. In the first case, the phase rotation is transferred simultaneously, so the blue color will stand out. But if it is successful, it will be white. We can see that the white color gradually increases over time. Some of them turn blue after turning white because they are in the path of phase angle transfer of other qubit. The figure on the right shows this in 3 dimensions with a time axis. In this way, the parallel execution of the phase rotation gate has been accelerated, and the execution time of the entire quantum computation has been reduced, including the acceleration of other operations. This figure is a cutout of the Hubbard model calculation that we saw earlier. And we can see that the speed was increased by more than 10 times before and after the acceleration. Using this speed-up technology described so far, we have constructed a quantum circuit generator that automatically generates specific and efficient operation procedures for qubits based on our quantum computing architecture. By creating a system that converts logic gate to physical gate in an integrated manner, we have established an implementation method for the early FTQC era, which is expected to be realized as early as 2030, when tens of thousands of qubits may exist. Finally, the effect of improving the accuracy of phase rotation and establishing the implementation method described so far are explained. In this project, we estimated the number of qubits and the computation time required for Hubbard model computation with our quantum computing architecture, and we were able to obtain an estimate that quantum advantage can be achieved with tens of thousands of qubits. The calculation time of a model with 6x6 crystal lattice with 40,000 qubits is equivalent to the current computer, and an 8x8 lattice with 60,000 qubits would take 10 hours, compared to 5 years for a current computer. That's 100 times faster. It is often said that in FTQC, quantum advantage typically requires 1 million qubits, but 60,000 qubits is an order of magnitude less. Tens of thousands of qubits are not yet in the world, but it is said that they will be realized as early as 2030. And this is the first time that we have shown the way how to achieve quantum advantage. In the future, we will further develop our architecture and expand the scale of computation. At the same time, we are moving forward with implementation on actual quantum devices, and we believe that it can be applied to condensed matter physics, quantum chemistry, and even quantum machine learning. So we would like to advance our effort in those areas as well. This is the end of my talk. Thank you for your attention.